Hi everyone. I'm Ankit. I'm starting to make YouTube videos on Leetcode problems and solving them so that if any other user want to solve them and they want some help, they could look at the video. Also, they I could find very less videos of solutions in C++, so I will start by doing it in C++. Uh, let's dive into my first problem, which I'm going to make a video on. This problem is odd even jump. I've seen in a couple of interviews this question, so I think this is a good starting point for me, and it could be helpful to you as well. This is because a hard lead code problem. So let's dive into problem without wasting much time. So let's state what is given in the problem. So the problem states that we have an array ARR which contains elements from 0 to 10 raised to power 5. So I'm just describing the problem here. The ARR value, ARI value is like from 0 to this. So what what the problem requires us is that we start from an index in the array and make a series of jumps. If we can reach the end of the array, then that index is a good starting index, right? Now there are few rules we have to follow when we are jumping from one index I to other index j. Those rules are following. Like when we are making odd number of jumps, so like for odd number of jumps, these are like the first jump, third jump, fifth jump, etc. We have to move to a index whose element is greater than or equal to the index which we are to represent, and also it should be the smallest possible value. So it is basically the smallest value which is greater than or equal to the value present at the index I, and we can only move to an index which is greater than the index I. So we cannot go backwards in the array, we can only move forward. If there are no such indices, then we cannot move ahead from that index. So for example, if we start with an array such as this, where all the elements are either less than the given index, if we are starting from the 0th index, all the elements in the subsequent indices are less than this, so we cannot move ahead of this 11 value, right? But if there is some element in the array like 12 or 11 itself, or like 13 then 11, then we move to the index whose element is greater than or equal to the given element, that is 11, and it should be smallest such value. So 12, 11, 13, 11, all of these values are either greater than or equal to 11, and the smallest of them is 11. So now there are two such 11s, so this problem states that we have to choose the index which is smaller for if the uh, both indices are same. So in this if we start from 11 and we have to make our first jump, we will jump to the fifth index which is 11, and then we will move to the second jump. So for the even number jumps, for like jumps like even number jumps is like the jumps like second, fourth, and sixth, the rule is that we have to move to an index in the array whose element is lower than or equal to the element present at the current index, and we have to choose the largest such element. If we have multiple such elements, we have to choose the smallest index, right? And in this also we can only move forward, we cannot move backwards. So if we take the previous example, earlier our index was if we started from index 0, made our first jump to first jump to index 5th, right? Index 5. The next jump, which will be the second jump, which is an even number jump, we will have to see which of the following values, like 13 and 11, which of them are less than or equal to 11. This is 11, and it is the greatest such value because that is just the only value here. If we had like more elements, which was like 9 here and then 10 here, then we would have like to make the choice between 9, 10, 11, and the greatest value of them is 11. So we would make our second jump to element index 7, right? Now let's think, how do we want to solve this problem? We know that uh, so like we want to reach the end of the end of the array, right? So we know that if we move from any element, we have to first make a jump to an element which is just smaller than the current element. If we are making like the second even number jump, if we are making an odd number jump, we have to make the jump to the element just greater than or equal to the current index. uh so yeah, if we now let's break down this problem. What do we want to solve here? Like if we are starting at, let's say, a current index as 1, like at index 2. So uh we want to find out whether we can reach the element 10 from element 2, and if it is possible, we would like consider this element, the first element, as good index, and we would like to know how many good indices are there, right? So if we are, let's say, starting from any index I, we want to know whether we want to first go to an element, an index which follows the rule of jump, and the most important thing here is that it is very deterministic to know which element we can go from a current index if we know whether it is an odd jump or even jump. So like if I am at index 2 and I have to make an odd number jump, like first, third, or fifth jump or seventh jump, we know for sure that which element it will go, irrespective of whether it is like the third jump or fifth jump. The state remains the same. So for index 2 and odd number jump, the state is the same, right? So we can define two states for each index here. Like for index I, we have two states, whether we reach that index on we reached that index on even number jumps or odd number jumps, right? Odd jumps. If we reach that index from odd jumps, we have to satisfy the rule of even jumps, and if we reach that index on even jumps, we have to satisfy the rules of odd jumps, right? And so now if we think of this problem as a recursion, you can think like, if you are at index I, you know which index j you have to go. If you know the state where you are, like index I, whether it's an odd jump or even jump, so from there you know where you have to reach next, and then your problem just gets defined to the array which is present for the indices greater than j. So like if you moved from I to j and in even number of jumps, so now you have the sub problem where you have to find good indices in the sub array j to n, and your state is odd jump now because you have to make the odd jump from here. So you get that we can resolve this problem into sub problems which which are overlapping. So if you start from 11, you might reach this 11, and then you will have to check for this subarray. And if you start again from, say, 5, and you reach the first jump, after first jump you reach, say, not let's say if you start from, there was an index j here, there was an element j here, you start from 10, then also you will have to, next, for the next jump you have to start from 11, right? If there's no 10 here, then, so you see that we have to calculate the whether the jump from 11 is possible multiple times. So here comes the concept of dynamic programming, that we store the state which we are going to see later, so that we do not need to compute it again and again, right? Because if we are computing it again and again, time complexity of the problem increases, and that is like that would not basically make this problem solve pass on Leetcode, and as well as that is not a optimized solution. So that's where we get the understanding that these problems need dynamic programming. Best way to think whether a problem needs the dynamic programming or not is to first look at the problem, divide it into sub problems, and if you find that there is overlapping sub problems, like here is the case where whether you start from 11 or whether you start from 10, you reach the second index 11, and then you have to solve the same sub problem of finding the or even number jumps. If starting from even number jumps, whether it is possible to reach 9 from this 11, right? So here we can see that there are where there are like the sub problems are overlapping here. So now let's dive into coding the problem. uh, Here we need to have array for storing the state for odd number of jumps and even number of jumps. So we would create a vector of boolean form, and this is odd, and we can initialize it with n elements, and all of them are false, right? And then we have a vector of boolean for or even state, right? And here also we can initialize with all the false. Now if we were at the last index is a good index for both the case odd and even, whether we are at the state of odd jump or whether we are at state of even jump, because from the last index we don't need to make any jump, right? So odd n minus 1 is true, as well as even n minus 1 is true. Now let's see what we can think from here, how we can get optimally the smallest index which is greater than or equal to the given smallest element which is greater than or equal to the given element for the subarray which is ahead of the given index. And also how do we find the largest element whose value is less than or equal to the given element, and in the subarray we have to see is ahead of the index I, right? So best way to do that is using a map, because map stores the array in a form of tree, and there you can easily binary search and find such elements in log n time. Because if you like stored all of the elements present in the ahead of the given index in form of vector or in form of array, you would have to like do the search in like a on time to know whether that which element we need to move to next. If we sort that array every time, like it still require log n to sort. So the time complexity is always greater if we are using vector here. Like if I show you by example, so let's say you were at the element 11 here, so at the element 0, at the element 0, and you have to make the first jump. At first jump, you need to for first jump you need to find whether in the array this for first jump you have to find the smallest value which is greater than 11, smallest value greater than 11. 11. So you will see that if you want to find the smallest value greater than 11, you will need to search this vector and then like get to a point which like it will take o(n) time to search such value, which is also like greater than 11, or and also like which is smallest, a smaller smallest value. So a good starting point would be to get the dp from the reverse order, that we start from the last index, because if we are storing, like if we stored the state for subarray this 13 11 9, then for whichever point in this array we reached point 13, we can easily get the value of the next, whether the whether jump is possible from this subarray, right? So, and also like this value should be stored in a form where we can do binary search, so that the time complexity is less. So we will store all these indices in a map which stores which is implemented on a binary tree. So we will create a map here, map int index, and here we will store all the indices which is present in the vector array, and map that index as a value to the key of the uh, element at that index, right? So like we can do the mapping like for int I is equal to 0, I is less than uh, array dot size. Let's initiate array dot size as n, and then let's do I plus plus and store this value in the index of array I. Index of array I is I, right? Now we have stored all the index, like we have done the reverse mapping in a map so that we can do a binary search for our rules for odd number jumps and even number jumps. Now let's start making these dp tables of odd and even from the reverse order, because as I explained earlier, if we have like the elements stored at from the back part of the subarray, we can easily get that value if we start from an index before there and reach into that subarray, right? Like it's a bottom up approach for the dynamic programming. So let's start from the index I is equal to n minus 2, I is greater than equal to 0, I minus minus. We are moving in the reverse order and decrementing the value of I. So yeah, now the odd. Now if we want to check the first, if it is a odd jump, we have to make an odd jump from the ith index. We have to check if in the like we do not need to initiate it first. We will initiate it with the with our indices so that we can know the exact value. Yeah, let's just start it. From first we have to find in the given map. So let's also insert index array n minus 1 is n minus 1. Let's insert the last element into the index, because we need to search that when we are moving from n minus 2th element, right? So yeah, we need to find for I is equal to n minus 2, or with whichever I we want to start, we have to see for the I is greater than, for the j greater than I, which of the element is either following the odd number jump rule or following the even number jump rule. So we will make two cases here for storing both the states. So yeah, let's do it. Yeah, yeah. To odd it is equal to so I'm you going to use two of the common functions in STL maps, which is provided in C++, which are lower bound and upper bound. So what does lower bound do? A lower bound finds the element which is first element which is greater than or equal to the given element, right? So in the map, it will look for the key which is greater than or equal to the given element, that is array I. So if we are starting from the back end, like we are checking from n minus 2, the map will only contain one element which is array n minus 1, and it will check if it is greater than or equal to array n minus 2, right? And if there are more number of elements, like from array j to, if the subarray stored in the index map is array j to array n, it will search in o log n time that which of the uh, value is either greater than or equal to and has the smallest value. So this will search the map in this lower bound. Uh, so yeah, so let's dive into this. So lower bound, what lower bound does is that it finds the key which is just greater than or equal to the given element which we are trying to search. So it will return the lower bound for array I in the index dot lower bound, right? And we check if the odd iterator is not equal to index dot end. End returns the iterator which is next to the last element. So basically, end doesn't point to any of the element, and if it reaches the end, that means that it is not able to find any element, any key in the map which has the value which is greater than or equal to the given array I. So if we are able to find such value, we will make the case that odd of odd of I is equal to, right? Odd of I is equal to even of odd iterator dot second. Second, basically we are using the second because we want to check the index j of that odd iterator. The value is stored in the key, and the element is stored in the key, and the index is stored in as the value of the map. So we will do this thing. Yeah, if now we check if the odd I is true, then we will have to also keep a counter of which are the good indexes. Int good index. So we start by, like, the last element is always a good index, so we start by good index is equal to 1. So if odd I is true, we will increment the good index because we can start our first jump from I. So we will increment it, right? Now we have to do the same for even jumps. Even iterator is equal to index dot upper bound array I. So upper bound returns an element which is strictly greater than the given, returns the key which is strictly greater than the given value which we are trying to find, and is the smallest such value. This is also like does the binary search, so it is also in log n time. This also search in log n time. So yeah, now so in this case, if that key is the starting of the map, so if that key is the smallest value, then it's of no use because we want to find the key which is smaller than or equal to the given array I, right? So we want the element which is just before the upper bound. So if it is the beginning of the map, then we have not found any such key, right? So we will search that even it is not equal to index dot begin. Begin point to the first key of the map. So that's why we are using begin. So if it is not equal to begin, that means we are not able to find any element, any key in the map which is less than or equal to the array I, right? So we are doing that. If it is not index.begins, does that we find some uh, index which is less than or equal to the array I. Basically, this even it will give the strictly greater than value. So the value which is, so the iterator which is before that will be just equal to or less than array I, right? So we will store that value in the even I is equal to. We will check if from that index we can reach the end. Like this, the if the boolean value of that is true, then even I will be true. Like if we can if we are starting from odd jump from the even iterator and reach the last index, then if we are starting from a ith index and makes even number of jump, then we will reach the last index as well. So it will be even it the second, right, right. Yeah, now we do not need to increment the good index counter here because it is for the even number jump. So if we can reach the ending index, if we are making the even number jump from the element I, from the index I, then it is not guaranteed that it will be a good index, because we want to know good index is the place from where we make the first jump. First jump is the odd jump, right? So here we do not increment the good index. All right. Yeah. So I think this is good enough. So if we iterate from all the indices from the backwards and reach the index 0, then we would have counted all the good index, because we have already counted the last good index, last index as a good index. We are starting our counter with 1, so we will return directly the good index. Now let's see if it works. Okay, we have a problem. We have not defined n, right? We have to define n as array.size before. Let's do that. So now let's run this. All right. Mm, what? How we can resolve this thing? Mm, oh yeah, we have to find the iterator before the upper bound, right? As we mentioned that we want upper bound gives us the element which is strictly greater than the give us the key which is strictly greater than the given element which we are trying to search, and we want to find the value which is smaller than or equal to and having this largest value. So we want to find the index just before that. That's why we have to do even it, decrement the value of even it by 1. Now let's try. Oh, okay. mm, Storing the map, right? We are storing the map. Index array n-1 is n-1. Let's debug this problem together. Okay, so we have initialized the vector with all false value, initialized the vector of even with all false value. We mark the mark the value for n-1 for both the cases, odd and even, as true, because the odd and even both the values from both the case, we can reach the last element for the last element itself. So that makes sense. We push that last element into the index map and increment the good index count by 1, right? And yep. Oh. Okay, so now we reach I is equal to n minus 2, and we are decrementing the I, so that is also right. If the odd iterator is index dot lower bound array I, that is also correct. Okay. Let's just print something here. See out odd it dot first and also array I, and we want to check whether it was odd number jump or even number jump. Similarly, we would want to search this for the even it iterator dot first array I, and we could mark it as even. And let's just check what are the outputs here. For 15, for 14, the 15 is the odd jump. For 12 also, no, no. Okay, we are not storing this value, right? We also need to store, as we move on in the array, we also need to store that value, right? Because we can clearly see that for 12, the odd number jump should be 14. It is clearly going outside of the bound. That's where I recognize that it is not storing the 14, it is directly returning 15 in this case. See, every element, the odd number jump is storing 15. That means we are not storing rest of the indices in our index map. So we should include those as well. Index array I is equal to I, right? Okay, now let's try to run this without this. Let's comment it out. Try to run it. Yeah, I think this is the correct now because we have debugged the cases which we were making incorrect in our first attempt. Now let's try to submit this. Yeah, it does work and it is having a quite a good runtime and memory usage because it is beating quite a lot of users. So I think this is a very good problem to like understand how maps work, time complexity of different functions of map, and also like how to think of the dynamic programming problems, like dividing the problems into sub problems and think of the states which we are going to make uh, the next move for. So I think this was a very good problem for understanding a lot of concepts. Thank you very much. Happy coding. Enjoy your day.